This is day 22 of Advent of Cyber 2024, and this challenge is called It's Because I'm Cubed, Isn't It? The learning objectives for this challenge are to learn about Kubernetes, what it is and why it is used, learn about DFIR and the challenges that come with DFIR in an ephemeral environment, and learn how DFIR can be done in a Kubernetes environment using log analysis. So for this challenge we need to start the virtual machine, and it will open up in split view. Back in the day, it was very common for companies, organizations to use a monolithic architecture when building their applications. A monolithic architecture is an application built as a single unit, a single codebase, and usually a single executable deployed as a single component. For many companies, this worked and still does to this day. However, for some companies, this style of architecture was causing problems, especially when it came to scaling. The problem with monolithic applications is that if one single part of the application needs scaling, the whole application has to be scaled with it. It would make far more sense for companies with applications that receive fluctuating levels of demand across their parts to break the application down component by component and run them as their own microservices. That way, if one microservice starts to receive an increase in demand, it can be scaled up rather than the entire application. Microservice architecture was adopted by companies like Netflix, which is a perfect example of the hypothetical company discussed above. Their need to scale up services dedicated to streaming when a new title is released, while services dedicated to user registration, billing, etc. won't need the same scaling level, made this microservices architecture a no-brainer. As time went by, companies similar to Netflix hopped aboard the microservices express, and it became very widely adopted. Now, as for the hosting of these microservices, containers were chosen due to their lightweight nature. Only, as you may imagine, an application of this scale required hundreds, even thousands of containers. Suddenly, a tool was needed to organize and manage these containers. And that's exactly what Kubernetes is for. Kubernetes is a container orchestration system. Imagine one of those microservices mentioned earlier is running in a container, and suddenly there is an increase in traffic. This one container can no longer handle all requests. The solution to this problem is to have another container spun up for this microservice and balance the traffic between the two. Kubernetes takes care of this solution for you, orchestrating those containers when needed. That makes things a lot easier for everyone involved, and it's because of this, along with the widespread adoption of microservice architecture, that Kubernetes is so ubiquitous in the digital landscape today. This popularity means that it's highly portable, as no matter what technology stack is being used, it's very likely a Kubernetes integration is available. This, along with the fact it can help make an application highly available and scalable, makes Kubernetes a no-brainer. In Kubernetes, containers run in pods. These pods run on nodes, and a collection of nodes makes up a Kubernetes cluster. It is within a cluster that McSkitty and Co.'s investigation will occur today. And DFIR basics. Every cybersecurity professional has stumbled or will stumble upon DFIR at some point in their career. It is an acronym for Digital Forensics and Incident Response. These two investigative branches of cybersecurity come into play during a cybersecurity incident. A DFIR expert will likely be called to action as soon as an incident is ascertained and will be expected to perform actions that will fall into one or both of the two disciplines. Digital forensics, like any other forensics discipline, aims to collect and analyze digital evidence of an incident. The artifacts collected from the affected systems are used to trace the chain of attack and uncover all facts that ultimately led to the incident. DFIR experts sometimes use the term post-mortem to indicate that their analysis starts after the incident has occurred and is performed on an already compromised system and network. Incident response, while still relying on data analysis to investigate the incident, focuses on responsive actions such as threat containment and system recovery. The incident responder will isolate infected machines, use the data collected during the analysis to identify the hole in the infrastructure's security and close it, and then recover the affected systems to a clean previous to compromised state. The incident responder can be seen as an emergency first responder whose aim is to contain the damage, extinguish the fire, and find and stabilize all the victims. On the other hand, the digital forensics analyst is the crime scene investigator, or detective trying to recreate the crime scene and ultimately find evidence to identify and frame the criminal. Both roles are expected to document all findings thoroughly. The incident responder will present them to explain how the incident happened and what can be learned from it, ultimately proposing changes to improve the security stance of the entity affected by the incident. The digital forensics analyst will use the findings to demonstrate the attacker's actions and eventually testify against them in court. In the task at hand, will you help McSkitty and Glitch become digital forensics analysts and retrace the malicious actor's steps? We will especially focus on collecting evidence and artifacts to uncover the perpetrator and present our analysis to Wereville townspeople. DFIR can be a lot of fun. It's It's easy to feel like a digital detective, analysing the crime scene and connecting the dots to create a narrative string of events explaining what happened. What if the crime scene vanished into thin air moments after the crime was committed? That is a problem we face regularly when carrying out DFIR in a Kubernetes environment. This is because, as mentioned, Kubernetes workloads run in containers. It's very common that a container will have a very short lifespan. In fact, in this year's Cloud Native Security and Usage Report, Sysdig found that 70% of containers live less than 5 minutes. So what can we do about it? Well, not to worry, it just means we have to expand our digital detectives toolkit. The key to keeping track of the ongoing and your often ephemeral workloads within your Kubernetes environment is increasing visibility. There are a few ways we can do this. One way is by enabling Kubernetes audit logging function that Kubernetes provides, allowing for requests to the API to be captured in various stages. For example, if a user makes a request to delete a pod, this request can be captured, and while the pod will be deleted, and logs contained within it too, the request made to delete it will be persisted in the audit logs. What request events are captured can be defined with an audit policy. We can then use these audit logs to answer questions which help us in a security DFIR context, such as what happened, when did it happen, who initiated it, to what did it happen, where was it observed, from where was it initiated, and where was it going. Of course, this just scratches the surface in terms of the level of visibility we can achieve in our Kubernetes environment. We can feed these audit logs as well as events from other security relevant sources into runtime security tools which help transform these raw events into actionable data, which can be visualized using yet more tools. So let's start our investigation. As mentioned before, some of the log sources would disappear as the sources like pods are ephemeral. So in our virtual machine, we'll open up a terminal. We will run minikube start. So it'll take roughly 3 minutes for the cluster to configure itself. So I'll come back when that's done. Okay, so it's now all set up. So let's see, kube ctl get pods -n whereville. We can see that all the clusters are running, containers are running. So if all the pods are up and running, you're ready to go. This will take another 2 minutes. Since we know that the web application was compromised, let's connect to that pod and see if we can recover any logs. So we will copy this command, paste it into the machine, then we will paste it into here. So with that done, we will try to output it to the terminal. So we've got the command, paste it there and paste it here, and we've got the logs. Sadly, we only see logs from the 28th of October, when our attack occurred later on. Looking at the last log, however, we do see something interesting with a request being made to a Shelley PHP file. So this tells us we are on the right track. Terminate your session to the pod using exit. Unfortunately, Miskitty knew that the log source was ephemeral and decided to ensure that the right backups of log source were made. Navigate to our backup using this. Okay, so we're within the Kubernetes thing, so we need to exit from like that. And now we cd to home, Ubuntu, then DFIR artifacts. Then inside of here we've got a few files, and the logs are stored in the pod Apache file. So let's output pod Apache, and apparently we'll be able to answer the first 3 questions. So let's do that. What is the name of the web shell that was used by malware? Assume that's shelly.php, which we can see here. What file did malware read from the pod? Let's try cat this, then do grep cat. See if there's any cat commands being ran in here. There is, and it's db.php. What tool did malware search for that could be used to create a remote connection from the pod? I saw it before. He used netcat, but I'll just bring up these logs again, and cmd which nc. So he's searching for the executable location of netcat. Cool. That's the first 3 questions done. So we'll go back up to here for what we should be doing now. So we now are looking at Docker, so Docker PS. There are two containers currently running. So it wants us to now connect to the instance. Which one? I guess it's talking about either of them. So we'll use the ID of the first one first. Okay, right click copy, docker exec, then ls-al file log. Doesn't seem to have been anything there, so we'll now check the other container. So copy the ID here, and now paste that into here and see if there's anything there. Yes, we have logs in the second container, but we can also then run docker logs and the container ID. So it's recorded all the logs for us. So these logs have been pulled for you and are stored in home Ubuntu DFIR artifacts in the Docker registry. So I guess clear and do cat Docker, and it wants us to, whoop, didn't mean to run that, so let's clear it again. Now do grep and search for head. Then we cut D space F1. Okay, so we're just looking at which IP addresses have made connections. So this 172 IP address is expected, as I'm pretty sure that's the IP address for the local Docker network, but we also have an IP address that is not used by Docker, so that is unexpected. So we are now going to look at the logs again. Let me clear this, do a similar thing again, but now we're just going to, actually let me just rerun that again, just to make sure what IP address it is. Okay, it is the same one that's listed there. So we clear, and now we're going to grep based on that IP address. So 10.10.130.353. So we've done that, and is there anything noteworthy in here? There's puts and post requests. So it's trying to upload a bunch of stuff, uploading to the wishlist web blobs. Maybe with this one we do a grep and do put or post or patch. Okay, well I tried and that didn't work. Let's just do put. So as we can see, uploading to uploads, then manifests. Let's try a post. Both to uploads again, then try patch, and same thing again basically. So what we will notice is the user agent in the request is Docker, meaning that this was a request made through the Docker CLI to pull the image. This is confirmed as we see several requests, then they download the image from this. Okay, interesting. So grep for patch, which we've already done. Okay, so MailMail was able to push a new version of the image. So this was explain how the web shell made its way into the image. Since MailMail pulled the image, made malicious updates, and then pushed this compromised image back to the registry, we used the information to answer question 4 through 6. So we'll do that now. What IP address connected to the Docker registry? That was unexpected. 10.10.13.253. What is the first connection that was made? So we'll go back to the grep and should be able to pipe to head 1. Oh, that should be dash N1 maybe. Okay, so what's it? So what time? Okay, what time is the first request? That is 29-oct-2024:10:06:33, and that is wrong. It expects the 000. There we go. What time is the updated malicious image pushed to the registry? So that was the patch. So that would be 29/oct/2024:12:34:28 and 000. I'll submit that. Okay, cool, correct. And I think that's the only one it can answer. So there's still one more, but we don't know that yet. So back to where we were now. So McSkitty was made aware that MailMail was given user access to the naughty or nice Kubernetes environment, but was assured by the DevSecOps team that you wouldn't have sufficient permissions to view secrets. The first thing we should do is make sure this is the case. So we will now do kubectl get role bindings -n whereville. So there's the mayor role. So kubectl describe role binding mayor user binding, and I spelt describe wrong, so to do that, mayor user binding not found. I need to do -n whereville. There we go, we've got that. So there is a role mayor user that's bound to this. So kubectl cube describe role mayor user -n whereville, and he has pods exec create get list describe get list watch, which seems to be fine. So all those except for permissions associated with pods exec. Okay, didn't see that. Pods exec. So allows the user to shell into the containers running within a pod. So to confirm our suspicion, we'll check the logs, which we will copy from here, paste into here, and paste back into the terminal and run. So a lot of this, a bunch of stuff in here. So get secrets. So the log snippet tells us the mayor attempted to get the secrets stored on the cluster but received a 403 as he didn't have permissions to do so. So get roles. So after being denied secret access, mayor then started snooping to see what roles were present on the cluster. Whilst running the previous get roles command, mayor malware will have found a role named job runner. These logs tell us that the mayor then described the role, which would have given him key pieces of information regarding the role. Most importantly for our investigation, it would have told him the role has secret read access. So get role bindings. Now, knowing this role can view secrets, MailMail tried to view its role binding to see what was using this role, and after seeing role binding named job runner binding, Malware described it and found out this role is bound to a server's account named JobRunnerSA. So here we can see the malware, now armed with the knowledge that a server's account has the permission it needs, lists all the pods running in the Werewolf namespace with the kubectl getpods command, and then describes the pod as morality checker. Then he would have found out that this pod runs with the JobRunner service account attached, meaning that if he were to gain access, he would be able to gain read access. And as mentioned in the role discussion, exec is permission usually not included in a non-admin role. It is for this exact reason that this is the case. McCity feels confident that the DevSecOps team had overly permissive role-based access control in place in the Kubernetes, and it was this that allowed malware to run an execute command and gain access into the morale checker. So if we now copy this command, paste and run, you can see access to resource secrets, pulls creds, and yeah. So see, Mail was able to run it, pulls creds. The final piece of the puzzle resolved around the secret. Finally, she runs the command and the attacker's path is confirmed. So we can get secret pull creds, and we can see, actually I'll clear this. If we run this again, we have username Miss Nice and password is Mr. Naughty. So that, okay, what is the value stored in the pulls cred? Okay, he wants the whole thing. So I have to copy all of this and then paste that here. And that is the last question answered. If you like this video, make sure to like and subscribe.